Hi everyone, now we are at unit number 3, Sequences and Series, lecture number 7. So I will start the session, some random doubts from the students in sequences. See, for example, the sequence is like this, sequence an, okay, sequence an which is 1 over n, 1 over n. So obviously the terms are 1, 1 upon 2, 1 upon 3, 1 upon 4 and up to so on. So this is an example of a decreasing sequence. But how to decide it is a decreasing sequence? See, you find out first term, second term, third term, fourth term like this, and you observe the terms. Okay, if a1 is less than a2 and a2 less than a3 and a3 less than a4, if this is an increasing sequence, right? This is an increasing sequence. If a1 is more than a2 and a2 more than a3, a3 more than a4, right, up to so on, this is a decreasing sequence, right? So this is decreasing sequence, okay, decreasing sequence. And what about this? And this is an increasing sequence, right? Increasing sequence, okay, increasing sequence. So when we can apply this formal definition, like see, already an is given, which is 1 upon n, and an plus 1 you need to compute, which is 1 over n plus 1, right? And I said in the last class you compute what is an minus an plus 1. So then you proceed like this. It is also, this is a formal proof. No need to approach always like this only. You can calculate the first term, calculate the second term, calculate the third term like that, and you observe the terms. Look at 1 by 2 means 0.5. So 0.5 is less than 1. Next 1 over 3, 0.33. 0.33 is less than 1 by 2. So indirectly this pattern is following, right? This pattern is following. Therefore it is a decreasing sequence. You can conclude like this also, no problem. But this kind of technique will not work out always. Why? Because if the sequence is like this, for example, if the sequence is, already we have seen, sequence an, which is sequence, okay, 1 over 1 into 2 plus 1 over 2 into 3 to n plus 1, okay, n into n plus 1. So if the sequence is like this, so then can you find out the terms? You cannot find easily the terms. So what is the first term? First term means n is 1. If n is 1, substitute here. 1 over 1 into 2. 1 into 2. Okay. This is first term. What is second term? Substitute n is 2, right? N is 2 means 2 into 2 plus 3. 2 into 3. 2 into 3. That means up to 2 into 3 we have to write. That means 1 over 1 into 2 plus 1 over 2 into 3. So this is second term. So this is like A2. This is like A1. Okay. Similarly, A3, again 3 into 4. Up to 3 into 4 you have to write. So 1 over 1 into 2 plus 1 over 2 into 3 plus 1 over 3 into 4. 3 into 4. This is third term, comma, up to so on. Now, here you need to compute the LCM here. Then you will decide what is A2. Then you have to compare. It takes time. Similarly, here also. You take the LCM and you have to simplify. Then only you can compare with A2. Okay. Sometimes the denominator may be large number. Taking LCM becomes difficult. Taking or simplifying this term A2 becomes difficult. So that comparison is difficult. What comparison like this? A1 is more than A2, A2 more than A3 like this, or A1 less than A2, A2 less than A3 like this. So comparison not always simple. For this kind of problems, so now this technique will work out easily. An minus An plus 1 will work out easily. This one will work out easily. That's why this is a standard procedure. Conclude about increasing and decreasing of a sequence, or we can compare like this also, no problem. Clear? Next one. And yours, the second doubt is, does a sequence converges to upper bound? See, the simple one. For example, let us take the sequence 1 by 1 only. 1 by n only. Sequence 1 upon n. 1 upon n. Let us take this sequence. Okay. So now I clearly can say that 1 upon n since n belongs to natural number set, right? N belongs to natural number set. So therefore this is always less than 1 only. This one less than or equal to 1. Sorry, less than or equal to 1. Whatever n you keep here for all n belongs to natural number set, this is true. N is 1, 1 by 1 less than or equal to 1. N is 2, 1 by 2 less than or equal to 1, 1 by 3 less than or equal to 1, always true. And at the same time this is more than or equal to 0. Okay, done, over. So 0 less than or equal to 1 upon n, that means an is less than or equal to 1. Okay, for all n belongs to natural number set. Now this is an upper bound here. This is an upper bound. Doesn't mean that the sequence converges to 1. But the sequence converges to which number? But the given sequence 1 over n is converges to 0. It is converging to lower bound. And don't ask a question, sir, can you say that does a sequence converge to lower bound? It is not always true. The statement does a sequence converge to upper bound is not always true. When it is true for only some sequences. For example, let's say sequence an is, let's take the sequence 1 minus 1 over n. Let us take the sequence. Okay, what is the first term? 1 minus 1, 0. Second term, half. Okay, these are increasing sequence. Look at third term, 2/3. Okay, fourth term, 3 by 4. So like this. So this is the sequence. Now at what number the sequence converges? The sequence converges to 1. Now for this sequence, so clearly 1 minus 1 over n, you are subtracting a positive number from 1. But 1 by n is always less than or equal to 1, right? So this is less than or equal to 1. Because we are subtracting a number from 1. Therefore this quantity is always less than or equal to 1. Now since the terms are positive, therefore more than or equal to 0. Therefore here 1 becomes an upper bound, 0 becomes a lower bound, but the sequence is converging to upper bound. For these kind of sequences, that means increasing sequence always converges to not upper bound, least upper bound. See, I can say that this one as like this also, or I can write, see, any number more than 1 is also an upper bound. So 0 less than or equal to 1 minus 1 upon n is less than or equal to 2 also I can write. This is always true. The terms of the sequence are always lying from 0 to 2. It is true always. It doesn't mean that it is converges to 2, since it is an increasing sequence. So the statement is, the correct statement is, the increasing sequence is converges to least upper bound. Least upper bound, LUB. First you collect all upper bounds, in that you collect the least one. So here the upper bounds are for this particular sequence 1, 2, 3, 3.7, 3.5, whatever, 4, 4.1. Okay, all these are upper bounds up to so on. So many upper bounds exist if upper bound is exist. So in this, what is the least one? Least one is 1. So this is called least upper bound is nothing but supremum. Supremum means the maximum term in that sequence. So in this sequence, what is the maximum term? Maximum term is 1 only. That is called supremum. Okay. So what can I say now? Does a sequence converge to upper bound? It need not be true. If it is an increasing sequence, it is converged to least upper bound, not upper bound. Okay. I hope it is very clear. And if the sequence is like this, for example, sequence 1 minus 1 plus 1 upon n. Now it is decreasing sequence, right? What are the terms now? 2, 3 by 2, like this. So these are the terms. If you apply the limit, so therefore the sequence 1 over 1 upon n is converges to 1, is reaching to 1, is reaching to 1. As n becomes very large, the infinite position number will be 1. So therefore this decreasing sequence, at the same time I can say that 1 plus 1 over n is always less than or equal to 2 I can write, is always more than or equal to 0 I can write. So therefore upper bound is 2, doesn't mean that it is converging to 2. Okay, its upper bound is 2. We can write its upper bound 3 also, more than 2. That means 2 is the maximum term in the sequence. That's why each and every number is less than or equal to 2. That's why. So it is an upper bound, but doesn't mean that the sequence converges to 2. It is converging to 1 like that. So there is no relationship between converging point to upper bound and lower bound. Okay. Next, third and fourth questions. Does the limit of a sequence is supremum? Does the limit of sequence is supremum? Is not always true. Not always true. As I said just now, not always true. So if the sequence is increasing sequence, if the sequence is increasing sequence, then it is converges to supremum. Just now I told converges to supremum. Not increasing sequence and bounded above also, right? Sorry, and bounded above. Let me write here and bounded above. Let me do this because this is precise. Okay, and increasing and bounded above, and bounded above, and bounded above. Increasing bounded above, then it is converges to supremum. Supremum or least upper bound, LUB. That's it. Here also same thing. The sequencing is increasing, it doesn't mean that it is converges. Okay, it has to be bounded above. Look at it is bounded above by 2 in this case, or bounded above by 1, then only it is converges. For example, if it is not bounded above, look at the sequence n. Okay, what are the terms 1, 2, 3 and up to so on. This is increasing sequence only. It is increasing sequence only, but it is not converges. You apply limit n tends to infinity. What is an? Nth term is n. So limit n tends to infinity. What is n now? E is nothing but infinity. It is diverges. Okay, every increasing sequence need not be converges. It has to be bounded above, then only it is converges to its supremum or least upper bound. Clear? Next one. So same thing, does the limit of a sequence is infimum? It is also no, it is also same. It is not always true. Look at the examples here. If the sequence is decreasing and bounded below, same story here. If the sequence is decreasing and bounded below, then it is converges to its greatest lower bound or infimum. Okay, infimum. That's it. So today class is about series. So sequence completes with that. Now let us enter into series. Listen carefully. Okay. Each and every term you have to understand very clearly. If you understand the basics very clearly, then you can attack the problem-oriented things. Okay. Look. An infinite series of real numbers. Look at series. An infinite series. I'm using the word series. An infinite series of real numbers is the sum, SUM, sum of an infinite sequence of real numbers. Infinite sequence of real numbers. If n is running from 1 to infinity, this is an infinite sequence of real numbers. This is a sequence, obviously, because it is written in flower brackets. Okay, it is a sequence. What kind of sequence? Infinite sequence of real numbers. Then the expression a1 plus a2 plus a3 up to so on plus an plus up to so on. So you take the terms of this sequence. First term is a1, second term is a2, third term is a3. So here the terms are separated with commas. That will be in sequence. But what about series? It will be added like this. So a1 plus so first term plus second term plus third term up to so on. So this is called an infinite series. Series means addition, sum of the terms. Sequence means only individual terms separated with commas. So it is written in sigma notation as summation or sigma n is 1 to infinity an, nth term of the series, or simply series an I will write. Series an, it stands, n is running from 1 to infinity, n runs from 1 to infinity. And the term n is called the nth term of the infinite series here. So here this an is called, what is an? An is called nth term of the series. And here what is this an? This an is called nth term of the sequence here. Okay, here nth term of the sequence, here nth term of the series. Don't get confused with the sequence and series. Sequence means the terms are separated with commas. Series means we need to add all the terms. Okay, next one. From hereafter, a series means an infinite series of real numbers. Now I use the word only series. Okay, series means you have to think it should be infinite series of real numbers. So let me write sequence an means simply a1, a2, a3 and up to so on. So like this. This is called sequence. Okay. It is called sequence. Sequence. It is called sequence. Right. And if I write same thing but in sigma notation like this, it means A1 plus A2 plus A3 plus up to so on. So this is about series. So you need to do addition. So this is called series. This is series. So that is the difference. Okay. Now, look at the definition of nth partial sum. It is very important for a convergence and divergence of a series. Let the series let the series an is this a1 plus a2 plus a3 plus up to so on plus an plus up to so on. Okay. And what is a1 here? First position number. Second one is second position number. This a3 is third position number. Up to so on. What is this? Nth position number plus up to so on. See, terms are here infinity because n is running from 1 to infinity, right? So terms are infinity. That's why plus up to so on I'm writing dot dot dot. So, and I'm generating a sequence like this. Sequence Sn is nothing but S1, S2, S3 up to so on, Sn up to so on. So these are the terms of this sequence. But how these terms are defined, S1, S2, S3, look at. The first term of the sequence S1 is defined as, I'm taking A1. What is A1? Look at this series. The first term of the series I'm taking separately. I'm calling this one as S1. I'm generating a new sequence. Okay? Yeah. Now second term of my sequence S2 is nothing but A1 plus A2. That means sum of first two terms A1 plus A2. Only A1 plus A2. That's it. That is my S2. Similarly, S3 is sum of first three terms. Okay. So this is sum of first term. Sum of first term. Okay. First term. Sum of like this. Okay. So similarly my S4 is sum of first four terms. Okay. So like that I am generating the sequence, and similarly Sn means what? Sum of first n terms, A1 plus A2 plus A3 up to so on n. Sum of first n terms only. Make it very clear. So this is my sequence now. Okay, such kind of sequence Sn I am taking. So such sequence Sn is called sequence of nth partial sum. Okay, this is called sequence of nth partial sum. Which one? This one, sequence Sn, right? And Sn is called the nth partial sum of the series. This term Sn in general, if my an is my sequence, what I can say? An is a sequence, and this is called nth term of the sequence, right? Nth term of the sequence. Nth term of the sequence. This is nth term of the sequence. Here also same Sn is nth term of the sequence only, but particularly I am generating Sn as like this. Particular terms. S1 means first term of the series. S2 means first sum of first two terms of the series. S3 means sum of first three terms of the series. Okay, let me write here series of the series of the series of the series. It is also of the series. Okay, of the series. It is also of the series. First three terms of the series, like this. Okay, so such a particular sequence, for such a particular sequence, Sn is called the nth partial sum, or simply nth term you can say, but particularly nth partial sum. It is sequence of nth partial sum, and this is nth partial sum. Nth partial sum means first n terms sum. Nth partial sum. So why the word partial? Because you are not taking all terms, right? You are taking only few terms. That few terms are first n terms. That means you are showing partiality, right? Because you are not taking all terms. That's called nth partial sum. The word partial sum, nth partial sum. Okay. So next one, the convergence and divergence of series. This is the main thing. Yeah. Look at. We say that a series converges if the sequence of nth partial sums, which is nothing but this one, Sn n is running from 1 to infinity, is converges. If the sequence is converges, then you can say that this series is converges. So there is a link. So from now onwards, if I want to conclude the convergence and divergence of a series, first you need to develop a sequence of nth partial sum, or you need to construct sequence of nth partial sum like this, and if this sequence of nth partial sum is converges, then the series converges. And you know how to conclude a sequence is converges, already we have seen. So this is old concept only. Okay, the sequence converges, then the series converges. That's it, nothing else. There is no special concept for series. Okay, next one, if the sequence Sn, this is sequence of nth partial sum, so if the sequence Sn converges to a limit L, let's say it is converges to L, then we say that the series also converges, and which is converges to L. It's very, very important. So if the sequence of nth partial sum is converges to, for example, some number 2, then series also converges to number 2. That's it. So the sum is 2 indirectly. So series converging means what? Sum is 2. Sequence converging means what? A number which is at infinite position. That is means converging of a sequence, right? That will be a number which is at infinite position. But this is series convergence means sum of the infinite terms. Sum of the infinite terms is nothing but limit of this series. Okay, look at once again. If the sequence Sn converges to a limit L, then we say that the series is convergent and the series is converges to L. Okay, next one. Further, L is called the sum of the series. Look at, L is called the sum of the series, and we write series n is running from 1 to n to a n will be L. So this is the mechanism of convergence of a series. Simply look at, for example, a series is given to us, then we need to develop first what is the sequence of nth partial sum, and we need to convert the limit of that sequence of nth partial sum. If limit exists, then the series converges. If limit does not exist, then the series diverges. That's it. If the limit exists and limit is finite number, which is some, for example, number 2, then series also converges to number 2, like that. Look at, we say that the series an is diverges if the sequence of nth partial sum of the series is diverges or not converges. That's it. So that means here, let me write here, if the sequence, for example, if the sequence an, so if the sequence an which is converges to L, so then directly I can say that the series also, the series an, this is also converges to L. That's it, simply. Okay, or we can write that series converges to L means what? That is series an will be, the sum of all the terms will be L. Okay, so it means actually what is happening in sequence of nth partial sum. Let us look at sequence of nth partial sum is Sn. Okay, is nothing but S1, S2, S3 and up to so on. So these are the terms of the sequence, so nth term and up to so on. Okay, and what is S1? S1 is nothing but A1. What is S2? Is nothing but A1 plus A2. What are A1, A1, A2? A1, A2 are terms of the series only, right? Now what is S3? A1 plus A2 plus A3, like this. Okay, now sequence Sn converging to L means what indirectly? It meaning is what? As n tends to infinity, it meaning is what? It meaning is the number at infinite position will be L. That means, let me write like this: S infinity. What is S1? Number at first position. S2, number at second position. S3, number at third position. Like that. S infinity means number at infinite position. That is nothing but my L only, right? Okay. So now what is S infinity here? Now what is S2? S2 means A1 plus A2. S3 means A1 plus A2 plus A3. What is S infinity? Is nothing but A1 plus A2 plus A3 plus up to so on plus A infinity. Indirectly, this is nothing but all the terms of the series, sum of all the terms of the series. That's only. I want that value only. That value is nothing but what? Here I am saying L. That's it. S infinity is L. That's what I am saying. If the sequence of nth partial sum is converging to L, indirectly sum of the all the terms is nothing but L. That means series An is L. That's it. So this is the hidden meaning of convergence of a series. Listen carefully, understand term by term, then we get correct meaning of the convergence of series. Yeah, this is about convergence of a series. Look at one problem. Find the sum of the series or find the converging point of the series. Okay, this n is 1 to infinity. This is 1 to infinity. N is running from 1 to infinity. Okay, now according to methodology, so to say the convergence or divergence of a series, we need to develop the sequence of nth partial sum. Okay, what is sequence of nth partial sum? So here, so for example, let me write first the series An is series 1 over 2 raised n where n is running from 1 to infinity. This is my series. Now let us develop the sequence or construct a sequence of nth partial sum Sn. Okay, this is nothing but S1, okay, S2, S3, up to so on, and nth term is Sn and up to so on. Okay, now the sequence of nth partial sum converges, then the series converges, right? Now, so be a sequence of nth partial sum. Sorry, be a sequence of nth partial sum. Nth partial sum. Okay, nth partial sum. Right. So then, so what is Sn now? Sn is nothing but sum of first n terms, right, of the series a1 plus a2 plus a3 plus up to so on plus an. This is sum of first n terms of the series. This is called Sn, right? But what is that? A1. Look at from this. What is A1? This is an, right? So with an, nth term of the series will be an is 1 upon 2 raised n. This is nth term of the series. What is A1? 1 upon 2. N minus 1, right? Sorry, it is n minus 1. N minus 1. So this will be n minus 1, whatever. Okay, n minus 1. Then what will be first term now? So then substitute, yeah. Substitute n is 1 here in this. N is 1 in this. You will get 1 over 2 power 0. So 1 over 2 power 0. This is the first term. Plus second term, n is 2. 1 over 2 power 1. Plus 1 over 2 power 2. Third term. Plus up to so on. Plus what is nth term? Nth term is 1 over 2 raised n minus 1. That's it. So this is the nth term of the sequence of nth partial sum. Let me simplify this. So this is 1 plus 1 upon 2 plus 1 upon 2 square plus up to so on plus 1 upon 2 raised n minus 1. So limit n tends to infinity if Sn value is finite and which is some L, then the series also converges to that L. Now what is this limit? So limit n tends to infinity, right? 1 plus 1 over 2 plus 1 over 2 square plus up to so on plus 1 over 2 raised n minus 1. And one of the students are asking same problem, but she is asking only this one. Okay, so what is the limit of n tends to infinity? She directly written which is 1 by 2 power infinity, which is 0 she has written, but this is absolutely wrong. See, you are concentrating on last term only. Then what is this then? Then I ask the same question like this. Then what is the limit n tends to infinity? 1 over 2 raised n minus 1. Now this one. Now this one is that 1 over 2 raised infinity minus 1, which is infinity. Now we can say this is 0. It is correct one. But here only one term, right? You apply the rule. But here it is not like that. Okay? Limit n tends to infinity 1 plus limit n tends to infinity 1 by 2 plus limit n tends to infinity 1 by 2 square plus up to so on limit n tends to infinity 1 by 2 power n minus 1. Its meaning is that. Okay? So don't do that simple mistakes. Don't commit such kind of things. Okay? Yeah. So yes, here what is limit n tends to this value? So since it is a geometric series, right? Look at second term divided by first term is, so a2 divided by a1 is 1 by 2, right? And similarly a3 divided by a2. What is a3 divided by a2? A3 is 1 by 2 square and a2 is 1 by 2, which is again 1 by 2. Look at, we are getting common ratio. This is r, right? This is common ratio. So r is same. a2 divided by a1, a3 divided by a2, a4 divided by a3, a5 divided by a4. If all are same, then only it is geometric series. So this is geometric series with common ratio 1 by 2 with the first term. And what is the first term? A will be 1. What is geometric series? Series A r power n minus 1, right? So this is geometric series. First term is AR, A, second term is AR like that. AR square like this, plus up to so on, like this. So this is geometric series. Okay. So clearly this is a geometric series. Therefore, what is the formula now? Sum of first n terms of a geometric series. So A plus AR plus AR square plus up to so on plus AR power n minus 1. Total how many terms? R power 1 means it is the second term. R power 2 means it is third term. N minus 1 means it is nth term. Okay. So this will be A into 1 minus R raised n upon 1 minus R. So clearly R should not be equals to 1. If R is equals to 1, it will become 0. Something by 0 is infinity. Okay. So this is the formula you have seen already in PUC. So same formula I want to apply here. Okay. So since we know this, therefore directly I can say that, so limit n tends to infinity, n tends to infinity. So here 1 plus 1 over 2 plus 1 over 2 raised 2 plus up to so on plus 1 over 2 raised n minus 1. So this limit will be, what is this? A means what here? A is 1, right? A is first term is 1 and geometric ratio is half. Limit n tends to infinity. Yeah, A means 1 minus, sorry, 1 into, right? A means 1 into 1 minus, right? 1 into 1 minus, A means 1 here, first term is 1 minus R, common ratio is 1 by 2, 1 by 2 whole to the power of n. Okay, because R power n. So this is numerator 1 into, yeah, divided by 1 minus R, 1 minus 1 by 2. So this is the sum of the first n terms of the geometric series. So limit n tends to infinity, simplify this. So 1 minus 1 by 2 whole to the power of n divided by 1 minus half is 1 by 2. So now this is limit n tends to infinity. So 2 into 1 minus 1 by 2 to the power of n. Okay. Now you apply the limit. So 2 into, what will you get? 1 minus 1 by 2 to the power of infinity. 2 to the power of infinity is infinity, 1 by infinity is 0. So final answer is, this is 2. That's it. So therefore I can say that this, so therefore the sequence of nth partial sum Sn is converges to 2. So therefore the series An, it is also converges to 2. What is that series An? Series 1 upon 2 raised n minus 1, where n is running from 1 to infinity, and this is also converges to 2. Or simply I can write that series n is running from 1 to infinity, 1 over 2 raised n minus 1 is equals to 2. Sum of all the terms will be 2. So this is the conclusion. Hope you understood. Let me do one more for more clearance. So look at this series again. So n is running from 1 to infinity. It is running from 1 to infinity, minus 1 whole to the power of n. Again same story. So let take the series will be some an. Okay, so series, let me write bn. Okay, series bn is series minus 1 whole raised n, where n is running from 1 to infinity. So what is the nth term of the series? Nth term of the series is minus 1 raised n. So to say the convergence or divergence of this series, simply we have to look at the nth partial sum. So if we expand it, what will you get? N is 1. Now what will you get? N is 1 minus 1 plus n is 2 plus 1. Okay, plus n is 3 minus 1 plus n is 4 plus 1 plus n is 5 minus 1. So plus up to so on. So this is a series. I want what is the sum of these terms. You look at, if I take even number of terms, that means only 4 terms. If I take, what is the sum? Look at 4 term is 1, 2, 3, 4. That means this one, first one cancels with second term, and third term cancels with fourth term. Therefore I will get 0. If I take again 2 terms, first 2 cancel out, again 0. So if you take even number of terms in the sum, you will get 0. If you take odd number of terms, odd number means, let's say n is 3. N is 3 minus first 3 terms. These first 3 terms. Okay. Let me take these first 3 terms. Then what will you get? Minus 1 plus 1 cancelled, only minus 1 will remain. If I take 5 terms, I am taking odd number of terms, right? So first one cancels with second one, third one will cancel with fourth one, therefore fifth one will remain minus 1. So if you take odd number of terms, you will get minus 1. If you take even number of sums, you will get 0. That means you are getting 2 kind of sums. So here you are unable to find the sum actually. Okay. Let me conclude this by using the concept of sequence of nth partial sum. So let Sn be a sequence of nth partial sum. So then what is Sn? Sn will be a1 plus a, sorry, not a1, here b1 I need to write because I have taken bn, right? So b1 plus b2 plus b3 plus up to so. So first n terms of the series, okay, first n terms, okay. So, therefore, so this is the Sn. It means what? What is first one? Minus 1 plus 1 minus 1 plus 1 minus 1, okay, plus up to so on. The last one is minus 1 whole to the power of n. Okay, so this is the sequence of nth partial sum. Now let us find the limit n tends to infinity to that term, Sn. Now what is this? So limit n tends to infinity, all these terms, minus 1 plus 1 minus 1 plus 1 plus up to so on. The nth term is minus 1 whole to the power of n. This is nth term. Okay, so therefore, if I take, if n is, let me write clearly. So if n is odd, n is odd. If n is odd, what I will get? So this limit will be n is odd number. Odd number means let me take first three terms only. First three terms. Okay. So first one cancel with the second one, only minus 1 will remain like that. Or you take 5 terms, again you will get minus 1 only. If n is odd, you will get minus 1. If n is even, if n is even, the limit value I am writing is equal to means this is limit value, okay, limit n tends to infinity value, and n is even means let me take 4 terms, so all are cancelled out, so therefore I will get 0. So therefore two limits are existing. So therefore here, therefore the sequence of nth partial sum, the sequence of nth partial sum is converging to two different limits. So is converging to two different limits, two different limits, two different limits. What are the two different limits? Minus 1 and 0. Therefore the sequence of nth partial sum Sn is not converges, or simply diverges, you write, not converges, not converges. Therefore series Bn, right? Series Bn, which is series minus 1 whole to the power of n, is also not converges. Also not converges. So this is the conclusion. So directly you can say that it is not converges by the first step. Already I told you. Look at the first step. Here, this series means minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 up to so on. Okay. But what is sum? Sum will be two chances, either 0 or minus 1. If I take first two terms, 0. If I take first three terms, minus 1. 4 terms, 0. 5 terms, minus 1. Like that. If I take large number of terms, let's say infinite number of terms in this sum. So if that large number of terms, if the large number is even number, I will get 0. If the large number is odd number, then I will get this sum is minus 1. So there is no particular number. That's why this possibility, there are two possibilities for this sum. One is minus 1, other one is 0. That's why the sequence cannot converges. Okay. So this is about convergence and divergence. And one more, problem number 3. Find the sum of the series an. Series n is running from 1 to infinity n, right? So obviously, so directly by looking at it, we can say, so without going for sequence of nth partial sum and all these things, so series n is running from 1 to infinity. Okay. Now what are the terms from 1 plus 2? Expand the series. N is 1, 1 plus 2 plus 3 plus 4 plus, simply instead of n you write n is 1, 1, n is 2, 2, n is 3, 3, like that. So plus up to so on. What will be this sum? Obviously it will be infinity, right? Plus infinity only, because all are positive terms. So therefore clearly I can say that this series n is diverges, because it is not finite, right? This is not finite. This is not finite. That's why it is diverges. If it is finite, then it is converges. So it is diverges. or you can go to the sequence of nth partial sum concept. Okay, or you can conclude like this also. Or so let us write, let Sn be a sequence of nth partial sum. Sn be a sequence of nth partial sum. Nth partial sum. See what I am telling in the first method. Let's say this is first method. This is first method. And this is second method. Okay, this one is second method. Second method, right? First method and second method. See, this first method cannot work out always. For example, look at previous problem, second problem, first method work out here. Directly I can guess what kind of the sum. But if you look at the first problem, you cannot guess the sum. Look at the first problem. You expand it. What are the terms? 1 plus 1 by 2 plus 1 by 2 square plus 1 plus 1 by 2 1 by 2 power n minus 1 plus up to so on. What will be the sum? This sum you cannot guess exactly what is the sum. That's why I am adopting sequence of nth partial sum concept. So that is a standard concept, sequence of nth partial sum. So directly if you are guessing what is the sum, you can write directly. There is no problem with that. Okay. So here in this problem number 3, directly I can able to guess what will be the sum. So the sum will be infinite. That's why I am writing directly. Okay. Here that's why series an is diverges. Or you can do like this, sequence of nth partial sum concept. So what will be Sn now? Nth term, sum of first n terms, right? a1 plus a2 plus up to so on plus an, sum of first n terms of the series. What is a1 now? 1, a2 2, a3 3 plus up to so on. What is an? n. Now what is limit n tends to infinity? So limit n tends to infinity, Sn. So this is limit n tends to infinity. Now what is Sn now? Will be 1 plus 2 plus 3 plus up to so on plus n. Okay. Now let us apply. Now let us apply here the limit separately. So limit n tends to infinity 1. Okay. So limit n tends to infinity. So by sum rule, limit can be applied separately. Okay. And limit n tends to infinity number 2, right? Plus limit n tends to infinity number 3, like this. Actually it goes on like this. So therefore what will get? So 1 plus 2 plus 3 plus up to so on. What is the last one here? Limit n tends to infinity n, right? So up to so on plus limit n tends to infinity n is infinity. What is this value? Look at 1 plus 2 plus up to so on infinity is nothing but infinity only. So therefore the sequence of nth partial sum, so therefore conclusion, therefore sequence of nth partial sum is, it is diverges. It is diverges. Diverges. So therefore series an is nothing but series n is diverges, or simply not converges, diverges, like this. So this is the convergence and divergence of a series. Okay. So now let us have a theorem, a special theorem, geometric series theorem. This is, look at the geometric series. N is running from 1 to infinity a or n minus 1, which is a plus ar square, like this. You run n is 1 here. If you substitute n is 1, what will you get? 1 minus 1 0. So r power 0 is 1. So that's why first term is a. Second term, substitute n is 2 here. 2 minus 1 is 1. So ar. That's why is ar. Third term is ar square plus up to so on. So this is a geometric series. How many terms? Infinite terms. Look at here. N is running from 1 to infinity. Previous one only finite terms I have taken. ar to the power of n minus 1 I have taken. So finite term sum is a into, yeah, this is very clear. So if the terms are finite, obviously the sum is a into 1 minus r to the power of n divided by 1 minus 1. Sum of first n terms only this. But here not n terms, infinite terms are there. So therefore this is not equals to a into 1 minus r to the power of n by 1 minus r. Make it very clear. Okay, this is not equals to. If the terms are only n number, first n terms, then the formula is a into 1 minus r power n by 1 minus r. Clear? So this one should be very clear first of all. So this series of infinite terms. Okay. in which a and r are the fixed real numbers. A and r are fixed real numbers and a is not equal to 0. Okay, a is not equal to 0. Then the conclusion is the geometric series, this one is converges to a by 1 minus r. A by 1 minus r if modulus of r is less than 1. It means, or simply you write minus 1 less than or less than 1. Simply modulus of r less than 1 means minus 1 less than or less than 1. So that means the series converges means what? The sum of all the terms is nothing but a by 1 minus r. Second condition, if modulus of r is more than or equals to 1, then the series is diverges. Diverges means what? Sum is not finite. Either sum is unable to find or sum is plus or minus infinity. Divergence means sum is unable to find, like minus 1 whole to the power of n. Let us look at the series. This series is the sum is not infinity and not minus infinity, right? But you are unable to find. There are two sums, minus 1 and 0. That's why the series is diverges. So diverges means what? Either sum is unable to find or sum is plus infinity or sum is minus infinity. For this, listen carefully. Okay, yeah, look at the given series is series n is running from 1 to infinity, a r power n minus 1. What are the terms now? A plus ar plus ar square plus up to so on. So these are the terms. Clear? Now look at the first one. What I want, I need to show that this sequence is converges to a by 1 minus r if modulus of r is less than 1. So condition, if modulus of r is less than 1. Okay, if modulus of r less than 1, then I need to proceed. So therefore, for convergence of a series, we need to look at the sequence of nth partial sum, right? So the sequence of nth partial sum is converges, then the corresponding geometric series also converges. So first let us generate the sequence of nth partial sum. So let Sn be a sequence of nth partial sum. Be a sequence of nth partial sum. Okay, sequence of nth partial sum. So now let me write what is Sn. Sum of first n terms of the geometric series, right? So what is the first n terms? So a1 plus a2 plus a3, okay, plus up to so on plus an. So this is first n terms of the series. What is the a1? First term is a, second term a2 is ar, third term is ar square, like this. So plus up to so on. What is the last one? ar power n minus 1. Okay, so if this sequence converges, then the corresponding series will be converges. Okay, now let me write this one as, so therefore what is the sum of this? So directly let me write here itself. So since, look at, only first n terms I have taken, right? These are first n terms. What will be the sum now? By using formula, first term is a and geometric ratio is r. Therefore a into 1 minus r to the power of n, because first n terms only, right, divided by 1 minus r. If first n minus 1 terms, if I take here power n minus 1, you write. If I am writing power n means r power n means this is sum of first n terms. If I write here n minus 1, sum of first n minus 1 terms. If the power is n plus 1, first n plus 1 terms. Which terms? Geometric terms only. So obviously the sum is this. Look at, I am taking only finite terms. Look at here, the terms are not finite, infinite number of terms. That's why this formula I am not using. Here terms are finite, that's why number of terms are finite. That's why I am using this formula. Now let us apply limit to this number Sn. Okay, so therefore limit n tends to infinity Sn value. So which is limit n tends to infinity. What is Sn now here? A into 1 minus r to the power of n, okay, divided by 1 minus r. Yeah, let me simplify this. So limit n tends to infinity, listen carefully. So a upon 1 minus r, a upon 1 minus r, okay, I am separating this, minus r to the power of n, a into r to the power of n divided by 1 minus r. Okay, 1 minus r. So here look at the first term not involving n. So therefore directly it's like constant a upon 1 minus r minus. So limit can be applied to both the terms by difference rule of the uh, theorem. You look at once, yeah. So limit n tends to a into r to the power of n upon 1 minus r. Okay, yeah. So therefore this one first one is simply a upon 1 minus r. What about second number? So this value I need to compute. So a upon 1 minus r I am writing outside completely because it is a number. Why? Because n is not involving. So the terms which are involving n we will write inside because limit n tends to infinity. Only r power n I am keeping inside. A by 1 minus r I am writing outside. So now my goal is what is the value of this? Okay. So since here r is modulus of r is less than 1, that is minus 1 less than or less than 1. So if r is lying in this interval, then what is the limit value? This limit value. Okay, so let me do it by case. So first case 1, what I am taking is 0 less than r less than 1 first. Okay, 0 less than r less than 1 I will do in case 1. Case 2 I will do minus 1 less than r less than 0 I will do. Then proof will become over. Okay, now first 0 less than r less than 1 and r equal to 0 also I need to prove. Okay, look at here. So minus 1, so here plus 1 it is minus 1. So open interval minus 1 to plus 1 I need to prove. So first 0 to 1 I am proving. Next minus 1 to 0 I will prove. Next at 0 also I will prove. Indirectly I am proving minus 1 to 1. Okay. First 0 less than r less than 1. What will be the limit value? So once 0 less than r less than 1. So then what will be the r? R is of the form. So it is a fraction only, right? It will be fraction definitely because it is less than 1. Any number less than 1 which is positive is fraction, which is look like this 1 plus some h, 1 by 1 plus h. Okay, where h is more than 0. Actually this value is directly 0 I can say, but proof I have not given in sequences, so I am proving here. I need to prove this value if r is minus 1 to plus 1. So where h is positive, you take any number instead of h. So this number is always more than 0 and less than 1. Therefore, the number is of the form 1 by 1 plus h if r is lies between 0 to 1. So the number can be expressed like this 1 by 1 plus h. Okay. Now, what is r raised n? Because I want here r power n value, right? Now I am generating what is r raised n. That means 1 over 1 plus h whole to the power of n, whole to the power of, and use binomial theorem what you have seen in PUC. So this will be expand what is 1 plus h whole power n? 1 plus n into h. Look at the binomial theorem, n into h. Okay. Now what is third term? N into n minus 1 by 2 factorial into h square. Okay, plus up to so on. The last term is h power n. H power n. H maximum power is n, right? So h power n. This is by using binomial theorem. So numerator will be 1. Since by using binomial theorem. Since by using denominator I am expanding by using binomial theorem, nothing else, by using binomial theorem. Binomial theorem. P1 sem 2, P2 sem 2 will be having binomial theorem, I think. Sem 1 or sem 2, look at binomial theorem. So by using binomial theorem, this is the expansion, right? So in the next step, you look at the denominator 1 plus, see all the terms are positive. Why? Because here h is positive, h is more than 0, right? And n is, what is n here? Let me write here. What is n here? So here n belongs to natural number set, right? index, n is index, so therefore n is also positive. N is positive, h is positive, therefore this is positive and it is also positive. Everything is positive. So all this sum of positive terms. Okay, so this entire thing is positive. So first term is 1, second term is nh, n it is, third term is n into n minus 1 by 2 factorial into h square like that. Last nth term is h power n. Now look at this, a crucial step. What I am writing is, so obviously, so 1 plus, look at the denominator, 1 plus nh plus n into n minus 1 by 2 factorial into h square plus up to so on plus h raised n. This is always more than or equals to 1 plus nh. Can I write 1 plus nh? Look at here how many terms, n terms I am taking, but here only 2 terms I have taken, first 2 terms. Only first 2 terms I have taken, 1 nh, 1 and nh I have taken, that's why this is less than always, right? So therefore, in the next step, so 1 over this one, 1 over all these terms, 1 plus nh plus n into n minus 1 divided by 2 factorial into h square plus up to so on plus h raised n. This is always less than or equal to 1 over 1 plus nh. Clear? Okay, nothing, just I am doing reciprocal, then equality will changes. But what is this? This is nothing but my Sn, right? This is my Sn. So Sn is less than or equal to, so clearly, so therefore I can say that Sn is less than or equal to 1 upon 1 plus n into h. So this will be upper bound, 1 plus nh. Since all the terms are positive, so since all the terms are positive, all the terms are positive, so therefore final conclusion is, I can say 0 less than or equals to Sn. That means Sn is more than or equal to 0 because all the terms are positive, therefore Sn is always more than or equal to 0, and which is less than 1 over 1 plus nh. Next, what I am going to do, can you guess? Pause the video and guess what I am going to do next. I am going to apply sandwich theorem. Okay, so look at upper bound, lower bound is converging to 0, and as n tends to infinity, 1 by infinity 0, so this is also go to 0. Therefore, what I can say, this is also go to 0. Okay, therefore by sandwich theorem, I can say that limit n tends to infinity, Sn value is 0. Therefore sequence Sn converges because 0 is finite. Sequence of nth partial sum is converges. Therefore series an or ar power n minus 1, yeah, let me write clearly. So this is ar power n minus 1 is converges to 0. Sin converges to 0. Therefore, this series is converges to 0 if, what is the condition? If 0 less than or less than 1. Okay, so now look at 0 less than or less than 1. This value is 0, right? R power n. So here, sorry, it is Rn, right? Sorry, it is Rn. So this is Rn. This is Rn. Let me. It is not Sn. It is Rn. Yeah. It is Rn. R power n. So therefore, this is also R power n. So this is R power n. Yeah. Should be very clear. Should be R power n. So therefore, and this is also limit n tends to infinity R power n. So this is, yeah, it is very clear, right? So therefore, by sandwich theorem, limit n tends to infinity R power n is 0. Next, I need to show that if R is from minus 1 to 0. So case 2 now, case 2 calculations, case 2. So if minus 1 less than or less than 0. Okay, already 1 less than or 0 less than or less than 1 I proved already. Now minus 1 less than or less than 0, right? I want what is limit n tends to infinity. Okay, r raised n. This is question mark. If r is from minus 1 to 0. Now what I am doing is, listen carefully. So what I am taking is, so if here is negative, r is negative completely, right? So let r is, let us write some minus alpha. Okay, for alpha positive, alpha is positive, minus alpha is always negative, right? If alpha is positive, minus alpha is always negative. That means what, r is always negative here, because r is minus 1 to 0. So therefore r is of the form minus alpha. So now let me compute what is r power n, which is nothing but minus alpha to the power of n. Okay, which is nothing but what, minus 1 whole to the power of n into alpha power n, isn't it? Okay. Now let us apply the limit. So limit n tends to infinity. Observe the terms carefully, what I am doing. So limit n tends to infinity. What is r power n minus 1 whole to the power of n into alpha power n? Okay. Now, yeah. What is alpha here? Alpha is positive. It's very fine. So once alpha is positive, minus alpha is negative, because r is always negative. But what are the r limits? R limits are minus 1 to 0. Then what will be the alpha limits? Can you guess? Alpha limits. So r is nothing but minus alpha, right? R is nothing but minus alpha. So can you guess at least minus alpha limits? Minus alpha is nothing but r only. R is from minus 1 to 0. Therefore minus alpha is also minus 1 to 0, nothing else. Simple. Now multiply it minus. So 1 is more than alpha is more than 0. So therefore alpha is lying where to where? 0 to 1. So look at, if these alpha from 0 to 1, if a number lying from 0 to 1, look at case 1. Case 1, what is the case 1? If 0 less than r less than 1, I proved that limit n tends to infinity, r power n value 0 I proved. Look at once, case 1 calculations. This is case 1. So same thing here, limit n tends to minus 1 whole to the power of n, alpha power n is there. If minus 1 whole to the power of n is absent, if this number is absent, then clearly it will be 0 by case 1. But minus 1 whole to the power of n is disturbing. So let us take the subsequence method. Okay, the limit value of this. So let me take the subsequence. So if this is a sequence an, so let me take an. Sequence an is minus 1 whole to the power of n, alpha power n. If this is my sequence, what is a power 2n? Minus 1 whole to the power of 2n, right? Alpha power 2n is nothing but alpha power 2n only, because minus 1 whole to the power of 2n is even number, minus 1 whole to the power of a number is always positive. So alpha power 2n. So now from this, so limit n tends to infinity, what is a to n is nothing but, so limit n tends to infinity, alpha power 2n. Now what is this? So this will be limit n tends to infinity, alpha square whole to the power of n. I can write like this, right? But this is 0 by case 1. Since by case 1. By case 1. By case 1, this will be 0, because if a number is from 0 to 1, then its raised n will be 0. Simply alpha is, you look at here, alpha is from where to where? From 0 to 1. Then alpha square also 0 to 1 only. Okay, therefore alpha square from 0 to 1. So first case satisfying, right? Condition satisfying. Therefore alpha square whole power n will be 0. And let us look at the second subsequence, a 2n plus 1. First two subsequence we have to take. So minus 1 whole to the power of 2n plus 1. So alpha power 2n plus 1. Now this will be minus alpha power 2n plus 1. Because why? Because minus 1 whole to the power of odd number is always negative. Now what is the limit value? So limit n tends to infinity, a 2n plus 1. which is limit n tends to infinity. What is a to n plus 1? Minus alpha power to n plus 1. But this is nothing but again same story, which will be 0. Okay, again by using case 1. Again, since by using case 1 calculations. By case 1 calculations, this is also 0. So therefore both the subsequents are converging to 0. Therefore the original sequence also converges to 0. Therefore this is equal to 0. Look at, for r minus 1 to 0 also I proved it is 0. Now the last case 3. What I need to prove? I need to prove for r is equal to 0. That's it. Then proof will become over. So r 1 to 0 I proved, minus 1 to 0 I proved, next r is 0. At 0 it didn't prove. Now let us prove r is 0. So now what is the limit? Limit n tends to infinity, r power n. Now this is limit n tends to infinity. 0 power n is nothing but 0 only, right? So this is nothing but 0 only. So in all the cases I got the limit value is 0. Then go back your statement. So what is this? So this value, if r is from minus 1 to 1, this value is always 0. I proved. Okay, assume this one equation number 1. So therefore equation number 1 implies, let me write here. So therefore equation number 1 implies, so limit n tends to infinity, Sn, right? Sn is equals to a by 1 minus r, right, minus limit n tends to infinity r power n. So this will be equal to a by 1 minus r minus 0. So answer is a by 1 minus r. That's it. So first proof is over. Okay, first statement is over. Now let us take second statement. Take it exercise, try once. What is second statement? If r is more than or equals to 1, the series is diverges. If modulus of r is more than or equals to 1, the series is diverges. Take this one exercise. Same we think like this. What I have taken, if r is 1 to 0 to 1, what I have taken here? If r is 0 to 1, I have taken, look at this. If r is 0 to 1, I have taken r is of the form 1 by 1 plus h. Same like this you think, then you will get the proof of the second statement. If r is more than or equals to 1, then the series is diverges. Okay, if r is modulus of r less than 1, the series is converges to a by 1 minus r. So just now we proved. So the limit value what I got, so sequence of nth partial sum. So here, so therefore here you write, therefore sequence of nth partial sum Sn converges to a by 1 minus r. Therefore the corresponding series also converges to a by 1 minus r if modulus of r is less than 1. That you have to write here. I am repeating once again. Look at the first statement. So limit n tends to infinity, Sn is a by 1 minus r. So therefore what I can write here? Therefore the sequence of nth partial sum is converges to a by 1 minus r. Therefore the series also converges to a by 1 minus r if modulus of r is less than 1. Okay, and with this I will stop.